That's a vacuum tube right there. I'm a big fan of vacuum tubes. This is not an ordinary vacuum tube, though. It's a Citron CE-A59-RX. Market value, I don't even want to talk to you about how much this thing is worth. What I do want to talk about is that it's actually a photoelectric effect tube. And there are two principal elements in it. The first one is this wire right here, and the second one is that big plate right there. We'll call it the plate of the photoelectric effect tube. And what's going to happen is I'm going to shine light on that tube, and there's a vacuum in there. That's why they call it a vacuum tube. Some people over in Great Britain call it a valve, which is kind of cool too. Props to them, because it does shut on and off the flow of electricity depending on what's going on. So it's kind of a clever name, like a water valve. But we call it a vacuum tube because it's a tube of glass that's evacuated. Cool. So you wouldn't want any air in here screwing things up. So that's why it's nice and nice. But light can get through here, and I've made this little screen so that only light going exactly the right direction gets to go through here. And I put this into this box, including with a power supply and stuff. And basically, I'll go from here, the real thing, to a schematic, and we can start talking about what the photoelectric effect is and what Einstein did to make it explained, which is pretty darn awesome. Here's the thing. There is a battery, or some high voltage power supply or whatnot. I don't even care what that voltage is right now. And then there's a plate of metal right here, which, as we saw in the tube, was a curved piece of metal, and we're going to call, no, sorry, that's the collector, is that wire that's very thin out here. This is the collector. And that's that's on the front of this tube, as you can see right now. And then we've got the emitter over here, and our emitter was a curved piece of metal. It designed, I mean, I'm going to kind of curve this one so that you see that the incoming light, probably we're going to have light coming from this direction, and it's all wavy, right? We got waves of light coming in this direction, and I'm going to call them photons. Because, well, this is really the essence of our problem here. Are they photons or are they waves? And who knows what's going on. But this is our emitter. And the emitter is connected to an ammeter right here. The ammeter will measure if there's any current going through. I guess if there's current going through here, then there'll be current going through here and here and here. So the ammeter is perfectly situated to tell us if there's any current in this photoelectric tube. And then we have to say that all of this stuff will be encased in glass. I need the collector and the emitter to be encased in glass. All right, the idea is this. When light hits the emitter plate, light comes in with some energy. And just like you, when you bail out your uncle again from jail, as soon as the jail is paid, does this make sense? I don't know, kinda. I don't know a lot about criminal justice. But as soon as the jail gets their money, then your uncle can go free. Maybe he'll have to stand trial and stuff too. But if there's sufficient energy in the light to free the, what do you think's gonna get knocked off? You know the structure of an atom, right? The structure of an atom's like, you know, some neutrons and some protons. And then way out here, I'm talking like way out here, and I don't really mean way out here like this. I mean like several rooms away at this scale. Way out there, there's an electron doing something. Guess who's going to get freed by the photons coming in, by the light coming in? It's the electron, of course. Don't be silly. So I'm saying that if there's sufficient energy, then electrons will be freed. And the cool thing about electrons is if they escape right here, excuse me, if they escape the emitter, then they will be drawn to the collector, because the collector is a positive place to go, and the emitter is a negative place to be. So they're going to be very excited about leaving. And in this tube, that looks like they leave this plate right here and they go to that particular wire that then collects them and dumps them over there into the power supply and ultimately through the ammeter, so we see some current. So we're going to be able to change the conditions of the power supply and measure the current that goes through, whether it is zero or big, or I guess it can't really be negative, but we're going to get currents. So here's what I'm saying. I'm saying that these electrons will be freed if sufficient energy exists to free them. They are trapped in their atoms on the emitter, and they can be knocked out if photons have enough energy. There are two predictions that classical physics makes. Those predictions are as follows. One, classical physics says that regardless of the color of light that you shine on the emitter, there will be electrons ejected as long as the intensity is enough. So, okay, let me see if I can summarize that. Regardless of frequency, electrons emitted if amplitude, because it's a wave, right, is big enough. That's my first classical argument, and that has to be the case because we've spent hundreds of years developing the idea that light is a wave. Back to Hören's principle, and all of this stuff comes to the fact that light is in fact a wave and not particles or bullets of light or something. Regardless of the frequency, electrons will be emitted if the amplitude is big enough. We have a freaking wave, people, and that wave is doing this if it's not a lot of intensity, and it's doing this if it is a lot of intensity. So this blue wave ought to be able to knock out electrons much more effectively than this blue wave right here. Secondly, watch this. Classical physics also predicts that the maximum amount of kinetic energy should increase if the amplitude is increased. So that means if the wave is bigger, we're going to emit even faster electrons. That's also very reasonable, right? So any given electron seems like it could have an arbitrarily large amount of kinetic energy. If we're putting in a really high amplitude wave, let's go crazy. We're putting in a really high amplitude wave. We could knock out your uncle. I mean, good luck knocking out your uncle. We could knock out an electron with an enormously high kinetic energy because that wave is hitting the electrons and it's making them zoom out really fast. So let me see if I can summarize this in a handy way. K max gets bigger as K max gets bigger as what? Oh, as the amplitude gets bigger. All right, I'm going to take a break. I suggest that you pause it and you guess what's going to be wrong with these two predictions. You kind of get the feeling that they're all completely nuts, but I want you to try to figure out what's actually happening based on a quantum understanding of light. If these light waves are in fact particles, what would that mean for the frequency and the amplitude's relationship? And what would it mean for the maximum kinetic energy? I'll tell you so you don't have to wonder too long, but go ahead, pause it again. Hi, just had a sausage biscuit from McDonald's and I'm ready to go now. These classical predictions are nuts. They're completely wrong. Regardless of frequency, an electron is emitted if the amplitude is big enough. If we've got particles, what the heck does amplitude even mean? Increasing the amount of light that hits the emitter means sending more particles in. And I think Einstein just finished saying that E is h times f. So in fact, the energy of every single particle is simply proportional to the frequency of the light that you're sending in. So if you want more light, you don't increase amplitude, you increase the number of photons, and you can send in photons individually, or you can send in billions of them at a time. Right now, you're getting hit by billions of photons from your computer screen. Or what? You're watching this on your phone? Aren't you cool? Okay. And look at this. Kmax gets bigger as the amplitude gets bigger. That's insane because these photons will be interacting with one electron and they will be sending their energy to one electron. And if you get more of them, that's what it means to get amplitude bigger. More photons will simply interact with more electrons, and you will get a greater current, but you won't have them going faster. Asterisk, how the heck do we tell how fast they are going? And I'd like to go into that by drawing this a little bit differently. Regard this battery. We're going to the next page. I'm going to draw a completely similar photoelectric effect setup, and I'll have the battery over here. We'll deal with that later. Here's the collector. Here's the emitter. We've got an ammeter here, and the battery is facing the wrong way. The battery says, no, don't bother coming over, electrons, I'm busy. So here is an electron, like here are these packets, these waves that are going this direction, but actually they're like wave packets. They are little bits, well, they're photons, let's be honest with each other. I don't know what the heck that means, but they are particle wave things. They're little blobs of energy, and their energy is h times f. Turns out Einstein's right. So what they're doing is they're hitting this emitter, and then an electron is freed, and chances are that electron will go any which way. That's fine. It just got freed by the the photon. It becomes what we call a photoelectron just because it's a regular electron that got freed by a photon. And that if the electron is going the wrong way, it'll just go thump. Remember, check this out. This is going to be negative now, and this side is going to be positive. Sorry about my throat. Wow. Maybe I should eat more healthily before making these lectures. Then let's say this other photon comes in and hits this electron, and this electron just happens to be aimed exactly the right direction. It's like, bam! And this voltage here, between there and there, there's a voltage, yeah? It's the voltage between this plate and that plate. We could call that a stopping potential. In fact, that is what it's called. Stopping potential is the voltage between those two plates, and it says to this electron, I don't want you to come over here. If you do successfully make it over there, then we will have a current. But there's no light coming on this part right here, so there's no way the electrons can come off of here and like do the effect backwards. So the only way we're going to get a current is if electrons do successfully A, get freed from the emitter, and B, happen to be pointing exactly the right direction, and C, be going fast enough so that their kinetic energy will transform into potential energy, and they will actually plomp onto, is that a word? Yeah, onto this collector right here. And that will be a measurable current. You can imagine there's a stopping potential where I can stop everything. There's also a stopping potential where I get just a few of them through. And that's what I'm particularly interested in. The stopping potential where they only just barely make it. And that's what I'm talking about with K max. The maximum kinetic energy then must be the charge times the stopping potential. Q times V, because that must be the change in potential energy of these suckers to go from here to here. They're gaining potential energy to go to this negative spot where they don't want to be. But if some of them happen to be pointing exactly the right direction and given exactly the right amount of energy, then they will make it over there. That's how we can measure the maximum kinetic energy of these suckers. So here's my plan. I'm going to refute both the classical predictions and tell you what actually happens. And then we'll see how quantum can explain it. This is the real result of this experiment. First of all, the light has to be the right color to eject electrons. You do not get any electrons out, even with no stopping potential. You don't get any electrons out unless the light is the right color. In fact, there is a cutoff frequency, and you know color is correlated with frequency, of course, so that means there must be a cutoff energy. That energy is a very interesting energy. So let me first say cutoff frequency, and I'll call that F naught. That is the maximum, the minimum frequency you have to have to free these suckers. What I mean is it's the minimum energy that you need to have. We could put little knots on here, the cutoff frequency and the, the cutoff energy. Cutoff frequency or higher needed to get any current Whoa, that is incredibly profound. They're saying regardless of how bright the light is, if I come in there with these different colors of photons, and I'm sending in a red photon, for instance, it may not emit any electrons at all. And then I switch to pink. Well, I don't even know what that's doing in there. I switch to orange, it doesn't emit any, and suddenly at yellow, it emits some. And the interesting thing is at yellow, it emits exactly the same number as at blue for the same brightness of light. Oh, that's really interesting. And purple also lets the same number of electrons out. So there's like, you gotta be at least this high energy in order to free something. That's like having just enough money to get your uncle out of jail. This is related to the fact that these electrons are bound in here, and if you don't hit them hard enough, they cannot get free. There's a wonderful video that says that there's a pit and the electron is a ball in that pit, and if you hit that ball, then it can make it out. If you don't hit it hard enough, it'll just go whoop up the edge a little bit and roll back down. The electron will remain trapped. But if you hit that sucker hard enough, it can go bam, and it will be free. And its maximum kinetic energy is given, well, we'll see a cool equation for the maximum kinetic energy. But I want you to understand that color of light, some colors emit electrons and others don't. And it also depends on what material we've made this emitter out of. Whoa, that's kind of funky. All right, so let's check for number 2. Just to re-emphasize number 1, brightness doesn't matter. It is only frequency. Whoa, that flies in the face of all classical physics, because brightness is amplitude. See the amplitude right there? Brightness is amplitude in classical physics. And if we talk about particles of light, we have quantized them, we're doing quantum physics, then we say that brightness is quantity. It's a whole bunch of photons rather than a whole big intensity of light, meaning a big amplitude of the wave. The second observable fact in the photoelectric effect, and we can literally do this in an AP physics lab, ain't no thing. The second observable fact is that if the frequency is greater than the cutoff frequency, increasing the intensity, like what I mean is we have enough energy to free these suckers. If we've got at least this much energy, so I'm going to say if energy of the light is greater than the cutoff energy of the light, or, oh, sorry, the parentheses should start there, or F is greater than F naught, increasing intensity increases number of electrons, not the maximum kinetic energy of the electrons. This also doesn't make any sense to a classical physicist, because she says, let's see, if we increase the intensity, then we'll be increasing the amplitude, so we'll be more likely to free electrons, and they'll be coming out faster as well. But the quantum physicist says, no, you've got that wrong. You need to understand that if I'm increasing the intensity, I'm simply sending more photons in. And so I will get more electrons out. But they will all be going the same maximum speed. I'm saying K max because there could be some other things going on. They might be going weird directions, or there might be some weird absorption or something. But there's a final awesome thing that comes from this photoelectric effect. So both of these say quantum is real and shove it, essentially. But let's get a little more space over here. And I want to say that you can make a graph now. I love graphs. I'm going to make a graph of, well, it's going to be frequency on the x-axis, and it's going to be the maximum kinetic energy, which, remember, we're measuring by the stopping potential. These super stubborn electrons are going to go the wrong way because they're kicked out of their emitter with so much kinetic energy that they do actually manage to go uphill, energetically speaking, and cause a current even when there's a stopping potential on. So we can measure the maximum kinetic energy, and the cool thing is, the brighter the frequency, these electrons do come out with a higher, did I say that right? What I mean is the higher the frequency, they come out with more kinetic energy. So you make a little graph right here, and you're thinking, well, if I use a sodium, check this out, if I use a sodium piece of metal in my tube, and that would be okay. Sodium's not very good if you're in air, but I mean, you could keep it clean in a vacuum, right? If you use a sodium piece of metal, you might get this pattern right here. You get some data and you find, whoa, if I increase the frequency, then I'm getting more and more energetic electrons spit out. Of course, if I get to this point right here, this I'm going to define as the threshold frequency, because at that point I'm getting maximum kinetic energy of 0. I'm not getting any electrons out right here. So then you'd find that to be the case. And if I take a different metal, let's say that I take a metal like gold or something and I make it out of gold, I get a very, very similar pattern right here, but it's got a different, what are you going to say? It's got a different x-intercept, which is F naught for gold. And I mean, we could look at this equation right here. This is a very interesting equation, but with this threshold frequency, we must mean something very different. I guess what I'm saying, let me define threshold frequency here. Threshold frequency is defined as, well, they call this energy, the threshold energy, they call it the work function. That's the energy that it takes to get the electron from here to here, and they use the letter phi for it. I don't really know why, but I'm just doing algebra on this guy right here, so I'm saying F is phi divided by h. So this defines what's called the work function. And you should think of the work function as the amount of energy required to bail your uncle out of jail. If the work function of energy is given to your uncle, then your uncle will be free. Now, if you give your uncle more money than the amount of money required to get him out of jail, then he will leave jail with some money. There's no problem with that, giving your uncle a little bit extra spending money. Maybe he needs to get some new pants. I don't know. Orange looks good on him, but not that good. And you know he doesn't want to wear what he came in with. So work function is, what am I trying to say? What I'm trying to say is work function is the minimum amount of energy your uncle needs. If you give him more energy, that is, you give him a higher frequency photon, then he will leave with more energy than, he will leave with some energy. He'll have some leftover energy. And I guess this is something to do with this energy right here. We could get an equation that acts like that. And I'm going to say that the maximum kinetic energy, watch this, K max is, well, it's the energy of the photon minus the work function. Our book actually uses a W naught, and I have never seen that anywhere else, so I'm not going to use it. I'm going to use the standard phi. The maximum kinetic energy of an emitted electron is the energy of the photon that came in minus the work function of the metal. And the work function of the metal isn't on this graph. But if I'm thinking about this graph in terms of y equals mx plus b, I want you to tell me where I can find the work function. I need you to look at this as if you just made this graph and that graph. And remember, these graphs are actually stopping right here. There is nothing going on below that. But I want you to find phi, the work function. Good luck. Please remember that this is a big part of understanding modern physics and why quantum mechanics was necessary. Do some problems, please, because you'll find the units of maximum kinetic energy are generally given in electron volts. If the units are electron volts, then I suppose, look at that, isn't that cool? One electron has an electron volt of 1 if it goes through 1 volt potential. So we can talk about its energy in terms of 1 electron volt if it manages to escape a 1 volt stopping potential. That's a really handy unit for the maximum kinetic energy. Could put it in electron volts right there. And that's probably how problems will be written for you. You should be practicing those. Stop watching videos. Do some problems. Goodbye. Sorry, one final thing on that graph. We made graphs of kinetic energy, maximum versus frequency, and they went like that. What's the slope here? Get it?